This is a presentation for comparing different image noise reduction filtering techniques. This video will take you through the presentation and then at the end show a demonstration of a MATLAB program that created the filters, implemented them, and then displays the resulting images. So, to start, this presentation goes through 4 different types of filters: a mean filter, a median filter, a wavelet denoising technique, and a morphological filter, and tests them across different types of noise. Now, the reason I'm doing this is to test which filter works well over which type of noise and see if we can figure out any advantages or disadvantages to the use of each type of filter. So to start, we're going to explain a little bit about each of the filters. Now, a median filter is a basic image processing filter that takes an array and an image array and then runs a structuring element shown there across it and returns the median value in this. So that way the assumption is if there's any noise it would create outliers, and taking the median value should reduce this noise. Now, this is going to return a grayscale image in our case. The next filter we'll be looking at is a mean filter. Now, this is very similar to the median filter, except instead of taking the median, it takes a weighted average of the surrounding pixels and returns that one. And in the same way, it should reduce noise outliers and give a better image reconstruction. Now, this also returns a grayscale image, so this mean filter will be compared against the results of the median filter later on. The third technique is a phase-preserving wavelet denoising technique, which takes the image and runs it through a wavelet transform and then uses multiple filter bands to try and reduce the noise in the image. Now, the output of this technique is going to be black and white, and the algorithm that runs the wavelet denoising automatically thresholds the image. Now, the hope is that in preserving this phase, that it will give the best possible reconstruction, because phase is one of the very important characteristics in any image. Now, lastly, we're going to be using a nonlinear morphological filter, which uses opening and closing, which are accomplished through dilation and erosion, to get rid of noise. Now, this takes a foreground element and actually expands and then contracts it, hoping to get rid of any outlier pixels or any holes in the image or in the background or foreground. So now that we've gone over a little bit of the filters, this is the image we're going to be testing. It's the facade of the La Sagrada Familia Cathedral in Barcelona. The image was chosen because of the complexity in it. There are lots of lines, lots of small details, and then a clear background and foreground. Now, this should make it easy to see how the filters are performing. The noise will affect the small details, and if the filters themselves end up blurring the details or deleting any of the edges or anything else like that. So here are the noisy images, and as you can see, there are different types of noise. Now, the first one is Gaussian noise, which just puts noise in the image based on the Gaussian probability function, and it's pretty easy to see, especially in the background. You can see the different amplitudes of the noise and how it's prevalent throughout the entire image. Now, the next one is salt and pepper, which essentially turns certain pixels on or off in a grayscale image that would set them to either white or black. And it's not as prevalent as the Gaussian noise, but the amplitude of the noise is much higher. Now, the next type of noise is Poisson noise, which is also made for the probability distribution function. And this one is of much lower amplitude than the Gaussian noise, but just about as prevalent throughout the image. Now, the last type is speckle noise, and speckle noise just takes each pixel and gives it a small variance, usually about 0.04 of the maximum amplitude. And so as you can see, there's a lot of noise in this image, and it's fairly blurry because of that. So now that we've created our noisy images, we're going to be looking at the results from applying the filters across them. And to start, we're looking at the median filter again. So with the Gaussian noise, the median filter got rid of a lot of the noise. It reduced the amplitude of a lot of the noise, as you can see on the image. And the background's an easy place to check for noise amplitude and stuff for that, just because it's a solid gray, so any variations there are easy to see. Now, there's still plenty of noise prevalent in the foreground too, though the details are fairly well preserved behind all the noise, but in all the image isn't very clean after the median filtering. However, the salt and pepper image run through the median filter looks almost exactly like the original filter, which makes sense because a median filter would take those outliers, they'd lie far outside the median, and as long as the noise wasn't too prevalent, it should return a pixel value close to that of the original pretty much every time. So the median filter does a great job of reconstructing the salt and pepper noise image. Now, the Poisson noise image, the median filter also filters out very well, though the noise amplitude was low in the first place, so it's to be expected that the filter would give a fairly good reconstruction. Lastly, with the speckle noise, the median filter does not seem to do a very good job at all. There's still plenty of noise present, and the entire image is in the foreground still very blurry, there's still noise everywhere. It's much harder to pick out the details, even compared to the Poisson noise image, the filtered Poisson noise image right next to it. Now, the mean filter. Now, the first thing to notice about the mean filter is that the edges aren't quite as sharp, which would make sense if it's averaging all the pixels. An edge between white and black would kind of be dulled to a gray, at least for a few pixels. However, despite this minor blurring, it does a very good job eliminating the Gaussian noise, probably slightly better than the mean filter, though we'll get to that later. The salt and pepper noise image is still very noisy. Because of the high amplitude, it still throws off the mean, because outliers will affect an average more than it will a median. The Poisson noise, the mean filter, also does a very good job of eliminating that low amplitude noise. And then lastly, the speckle noise. It's still a little blurry, there's still a little bit of noise in it, but in all, the mean filter does a decent job of making the image cleaner, if not reconstructing it perfectly. Moving on to the black and white filters, the first one we're going to be looking at is the wavelet denoising technique. Now, the wavelet denoising technique, the first thing you can see is, across the first two images, it does a pretty good job of keeping the detail in the image, especially with such a detailed image and changing it to black and white. It's hard to see simply because it's a black and white image, but much of the detail on the facade is still there in the pillars. The piping in the pillars is definitely one place where it did a good job of reconstructing it. Now, in each of these images, there's definitely some extra noise in the background, but all in all, the Gaussian noise was eliminated fairly well, especially in the foreground, and the detail kept very well. The salt and pepper noise, however, didn't seem to be eliminated at all. You can see it in the white dots all throughout the foreground and the background, and it's still a very noisy image. Now, the Poisson noise was eliminated fairly well by the wavelet denoising technique, except for, once again, the blotch in the background in the upper right of the picture. And same with the speckle noise. It did a great job of preserving detail, the piping on the pillars, some of the edges in the facade, some of the shadows. Once again, some noise up in the background, but not a huge detail because the foreground was preserved so well. Now, the last set of filter results is the morphological filter. As you can see right away, the details are nowhere near as sharp in the morphological filter, but there seems to be less noise in this one, especially in the background and in the salt and pepper image for sure. There's not noise all throughout the foreground and the shadows, the white pixels dotting the entire image. The Poisson noise is also gotten rid of fairly well, even if there is some slight detail loss. However, when it comes to the speckle noise, which remember was the high amount of noise in the image, it eliminated most of the details along with not getting rid of all the noise. All that's left is a shell of the former foreground, so it's hard to pick out any details or even tell what you're looking at in this image. So now that we've looked at all the results once, we're going to be comparing the filters side by side, the two grayscale ones and the two black and white ones. So for the Gaussian noise, as we said before, both of the filters do a pretty good job reducing the noise. though it's still apparent in both output images. And the mean filter, there's some slight blurring across the edges. The mean filter maybe a little too, but not as much. In all, both filters do a decent job of getting rid of it, but they could definitely be improved upon. There's still blurring, there's still noise in both these images. The salt and pepper noise, the median filter is almost a perfect reconstruction, whereas the mean filter blurs all the noise across the image and lowers the amplitude a little bit, but the noise is still very prevalent. It's probably seems as if there's more noise than just at a lower amplitude. So for salt and pepper noise, the median filter is better, hands down. For Poisson noise, both of the filters once again do a great job. The low amplitude noise, it's hard to see much noise in either image except for a little bit of pixelation in both of the backgrounds, but in all, both a median and a mean filter does a pretty good job of eliminating the low amplitude Poisson noise. Lastly, when it comes to the speckle noise, the median filter leaves noise all throughout the background and foreground. The amplitude doesn't seem to be diminished much. In short, the median filter doesn't do a good job, whereas the mean filter, you can still see the noise and there's some slight blurring, but in all, it's a much sharper image. The noise is nowhere near distracting as it is in the median filter. So in this case, at least just by visual preference, I would probably choose the mean filter. So in all, just some broad overarching thoughts after going through that, where the median filter seemed to eliminate smaller amounts of noise that was less prevalent a little better, such as the salt and pepper, and it did very well in the Poisson and Gaussian. But when there was a lot of noise in the speckle noise, it didn't do a very good job at all. The mean filter did a much better job with large amounts of noise, such as the speckle filter, and then also did well in the Gaussian and the Poisson as well as the median filter. But in terms of small amounts of noise but high amplitude like salt and pepper, the mean filter didn't do very well at all. And it always costed some of the detail in blurring some of the edges and things, which was acceptable with large amounts of noise, but in small amounts of noise it didn't really make sense to use a mean filter. Moving on to the black and white filters, it's going to be obvious throughout all these filters that the wavelet denoising technique, perhaps due to the automatic thresholding, did a much better job of preserving most of the detail, whereas the morphological filter has less noise in it. And it's easy to see throughout the center of the image and the center left that there's way more detail in the facade in the wavelet denoising technique. But the morphological filter did a great job of reducing noise, especially in the background, and even throughout the foreground, though some of the details gone, like the piping in the pillars and the facade in the center top of the image. Now, salt and pepper is kind of the outlier to these. The wavelet denoising technique did very little to actually filter the salt and pepper noise out. There's noise all throughout the image, and the detail is still there, but the amount of noise just makes it not a very pleasing image to look at. The morphological filter, on the other hand, did a great job, got rid of almost all the noise, and preserved a fair amount of the detail. Not all, once again, not as much as the wavelet denoising, but did well enough where the morphological filter is probably preferential in this case. Now, for the Poisson noise, they both did a very good job reducing the noise, except for the blotch in the background of the wavelet denoising technique. In this one, it's a trade-off of whether more detail and slightly noisier image is better, or less detail but almost no noise in the image is better, which would be the morphological filter. Now, the speckle filter, the wavelet denoising technique, is almost unquestionably better. It preserves most of the detail and gets rid of most of the noise in the foreground, even though there's quite a bit in the background. But the morphological filter, in this case, almost entirely destroys the foreground. It gets rid of most of the facade. You can't even see the shape, the outline of the cathedral very well anymore. So, in summary, like we've been saying, the wavelet technique preserved much more detail, but often created noise spots in the background and was actually, thinking back to the salt and pepper, poor at eliminating very high amplitude on and off noise. The morphological filter, on the other case, always eliminated the majority of the noise, but often at the cost of much of the detail in the photo, especially in the case of the speckle noise, where to get rid of the noise, it actually ended up getting rid of most of the detail in the picture along with it. So, in summary, different filtering techniques are required to filter different types of noise in images based on whether you think the noise in your image is closer to a salt and pepper, or a Gaussian, or a Poisson, or speckle noise. So to filter, you'd first have to try and model the noise as one of these, and then pick your type of filter and go from there depending on that. Another observation from all these filters is perfect reconstruction is very rarely possible, with the one exception possibly being the median filter across the salt and pepper noise. For the most part, filtering is an imperfect science. It is capable of getting rid of the majority of the noise, but there's always a drawback, such as the mean filter slightly blurring the details, or something to that effect. Now, for more information considering any of these filters, here are a few references going over first modern median filter techniques that will even do it for color images, the algorithm for the phase preservation in the wavelet techniques. The third one is a digital image processing textbook that the theory for this project was mostly taken from. And then lastly, a paper that outlines the introduction of morphological filtering, specifically to reduce noise in scanned images. So now that I've taken you through this presentation, lastly I'm going to give just a quick demonstration of my program. So as you can see, it's in the form of a MATLAB script, and just very basically it reads in an image here and converts it to reads in a color image and converts it to grayscale, and then uses a noise function to put the noise in it, and from there runs it through first a median filter in this section, and then a mean filter, and then uses a separate function, which I'll show quickly later, to do the wavelet denoising technique, which requires quite a few parameters from image power to number of filters to a threshold level. And lastly, through morphological filtering. And before the morphological filtering happened, the image had to be thresholded to make it black and white, so there would be a clear foreground and background. So that's what the for loop accomplishes, and then shows each of those images, and lastly implements the morphological filtering. Now quickly, this is the wavelet denoising function taken from Dr. Peter Kovesi of University of Western Australia. This, in short, although it's a very complicated algorithm, runs the image through a wavelet denoising technique and then runs it through a few filters later on in the program. And the log Gabor creates the wavelets, the log Gabor line right there. And then lastly uses statistics to apply a automatic soft or hard threshold to the image. Now, to see the script in action, we're going to run it. And as you can see, it pops up all the images, runs through them all, and this is the part where it's doing the wavelet denoising. It's a very complex algorithm that actually takes more than a few seconds to run. Then once it's through all these, it continues on through the morphological filter. And as you can see, it created the filters, created the noisy images, the Gaussian, the salt and pepper, the Poisson noise, the speckle noise, and from there ran the filters across them. So in short, this was the program and the way the filters are implemented. And this is all I have for filtering techniques to reduce noise in images. Thank you for your time.